So a lot of you were struggling with the in-class activity in 3D, so we're going to do a quick review of that. So the question was, determine the components of reaction that the ball and socket joint at A, the smooth journal bearing at B, and the support at C exert on the rod assembly. So I drew in all of the forces, right, all of the unknowns, and at some point we're going to have to solve for the sum of the moments and the sum of the forces in every single direction. Typically you start with the moment because that's where you're going to end up having less unknowns. So a lot of you guys also wanted to draw these moments in your diagram, and the reason why we ignore these moments is because they are basically these things that when we write our equation. So let's look at this, for example. So this moment here is a moment about the y-axis. When we solve for the sum of the moments about the y-axis, we are finding which forces are creating this moment here. So in the end, these forces that you end up drawing are basically, or these moments that you end up drawing in your diagram are the moments about the y-axis, are the moments about the x-axis and the z-axis, which you're accounting for when you do the overall summation of the moments. That's why you do not have to draw them in, because yes, they are unknowns, but you're not trying to find them. You're trying to find the unknown forces. So we ignore the moment drawings in there. Just keep your diagrams with the forces. So we know we're going to have to find some of the moments, some of the forces. Where do we start? So a lot of you are confused as to where to start. How do you know where to start? So the first thing I do is I look at every single axis. So let's start with the z-axis. If you start at the z-axis and you're looking for all of the moments about the z-axis, because these forces AY, AX, and AZ fall on the z-axis, we can ignore them. So the only unknowns we have then is BZ, BX, and FC. Alright, let's look at the x-axis. For the x-axis, once again, AY, AX, and AZ fall on this axis, so we can ignore them. And the unknowns remain the same, BX, BZ, FC. And then let's look at the y-axis. So when we look at the y-axis, these three forces fall on it, so we can ignore it, but so do these two forces, so we can ignore these two forces as well. Therefore, we only have one unknown. So if we solve for the moment about the y-axis, we're going to end up with one unknown, and we can solve for that unknown. So that's how I decided to start with the y-axis. So let's pretend that, or imagine that the y-axis is like this hinge, right? You hinge this plane to the y-axis. Or imagine that this entire thing is like a rectangular plane or a rectangular door that's hinged at the y-axis. So the only forces that will cause a moment on this plane about the axis are the perpendicular forces, so the 900 and the FC. So if we're hinged at the y-axis and we have this door or this plane, if we push downward on the door, it will start rotating. It'll start rotating, right? It'll push it downward, so you can imagine the whole plane starting to rotate about the y-axis. And because it's rotating in this particular direction, your thumb, using the right hand rule, would be pointing towards negative y. So we have negative 900 times the perpendicular distance, which is 0.4 meters. And then we look at FC. So FC would be pushing upward on the plane, so it would cause a rotation in the opposite direction. And that means your thumb will end up pointing in the positive y direction. So we're going to have a positive moment. So FC times the perpendicular distance, 0.6 meters. So you end up with this equation where you have FC as the unknown, and you end up finding FC equals 600. So it's helpful to imagine like you everything along this axis is hinged. It can't move, but you have this door that can revolve around the axis. So now I chose to look at the x-axis again. Now that I know my FC, I have two unknowns. I have bx and bz, and I can ignore these three because they fall on the x-axis. So, okay, so here, once again, I imagine like everything is hinged at the x-axis. So we have like a door hinge, and then everything else, this entire plane is like a door or a rectangular plane, right? So if I look at bx would end up pushing the plane this way. But it won't cause a moment about the x-axis because it's parallel to the axis, right? Anything that's parallel to the axis will not cause a moment. It must be perpendicular. So the only three forces here that cause a moment are the 900, the FC, and the BZ. And we know what FC is now, so our only unknown is BZ. So let's start with the 900. If 900 pushes downward on this plane, it's going to start rotating about the x-axis in a direction such that your thumb will end up pointing in the negative x. So we have negative 900 times the perpendicular distance, which is this 0.4 meters. And then if we look at BZ, if we have this rectangular plane and BZ pushes upward on the plane, it causes a rotation such that your thumb will end up pointing in the positive x direction. So we have plus BZ times the perpendicular distance to the x-axis, which is 0.8 meters. And then if we look at FC, it's also pushing upward on the plane, which will cause the same rotation as BZ. So it's also going to be positive. FC times the perpendicular distance, which is 1.2 meters. So we end up with, after solving for everything, BZ equals negative 450 newtons. So we drew BZ upward, and we get a negative number. That means that, in reality, BZ should be pointing downward. So BZ should be pointing downward with a magnitude of 450 newtons. Alright. So we've looked at the y-axis, we've looked at the x-axis. Now let's look at the z-axis. With respect to the z-axis, we have just found BZ, we have found FC, so the only unknown is BX. So that's what we can solve for, right? Because BZ and FC are parallel to the z-axis, they do not cause a moment about that axis. So the only force that causes a moment about the z-axis is bx because it is perpendicular to the axis. So if we look at this, and once again, imagine that z is like this hinge, right? And we have this plane once again. So if bx pushes on this plane, the plane will start rotating. Plane will start rotating about the z-axis such that your thumb will end up pointing in the negative z direction, so it's going to be a negative moment. So we have negative bx times the perpendicular distance, which is 0.8 meters, and because bx is the only one, we deduce that bx equals 0 newtons. Alright. So now we found bx, we found bz and fc, so we know these three. And we've done the sum of the moments about all three axes, so now we move to the sum of the forces about each axis. So I start with sum of the forces in the y direction. The only y force is ay. We have no other y force, so automatically we know that ay equals 0. From there, we move on to the x-axis. For the x-axis, we have ax and bx. And because we know that bx is 0, it turns out that ax is 0 as well. And finally, we do the sum of the forces in the z direction. So we have az, bz, fc, and 900. So AZ is pointing upward, so we do AZ plus BZ, because in our original drawing it's pointing upward, minus 900, because it's pointing downward, plus FC because it's upward. So then we plug in all of the numbers for all of our knowns, and we end up with AZ equals 750 newtons. And finally, we have found all of our unknowns. I hope that helps you guys visualize it a little bit better. And the best thing I can recommend is to think of a door that is hinged to a particular axis. So that'll help you figure out how is the door going to rotate about that axis. How is this plane going to move or rotate about the x-axis. And that'll also help you figure out your directions. And yes, I hope that clarifies things a little bit better.